We're going to continue with the theorems, but let's do a quick review. Last session or last class, we did 7 properties, or sorry, we did 7 theorems for the limit. We learned the properties and we learned how to use the direct substitution method. And today we're going to do a little bit more. You're going to learn 2 more methods, okay? I will do that one by one. The first one is called dividing out. Dividing out method or dividing out technique. Quick review. We know this already. What's the limit when x approaches to 5 if I want x squared minus 25 over x minus 5? You know this, right? Because we have a numerator, denominator, both a polynomial, so we call this as a radical. Remember, we call this as a radical function. And then we can just simplify that. Factor x plus 5, x minus 5, and over x minus 5. So this gets crossed out. You plug that in, you get a 5 plus a 5 equals 10. That's what we learned a little earlier. And that's when you find the limit, right? That's the 2 functions that agree at all except one point. That one point is 5. So it's very easy to do that. This method, it's called a dividing out technique or dividing out method. Sometimes you have this, it's very easy, and most of the time you can just factor and then get it. There are a lot of, I think there's a lot of exercise at the back of the book that you can do it. Now, I want to ask you or give you another example. I want to show you that if it's not as direct, if it's not as easy as factor, what are you going to do? This one. This is not a polynomial because it has a square root there. It's part of the radical. Radical and then minus a number, then divided by a polynomial, and the x approaches to 4. Okay, the first thing first, you always take a look at this first. We have something look like this. And x approaches to 4. Let's see what happens if I do direct substitution. X minus 4 give you 0. X plus 5 give you 4 plus 5. That's 9. Square root of 9, you get a 3. 3 minus 3. Hey, you get a 0 over 0 again. You have something look like this, okay? And that's, you got to do something. Now, if you have something look like this, it's a 0 over 0 type. And you have a square root, I want you to rationalize it. Okay, we call that a rationalizing method. Rationalizing method is this. You're going to multiply by, okay, when you rationalize by something, you're going to multiply by its conjugate, right? What is a conjugate? It's going to be this, x plus 5 plus 3. And if you multiply by something on the numerator, you're going to multiply by the same thing in the denominator. Okay, so this is a square root of minus 3. That's the square root of plus 3. After you do this, you get a difference between the 2 complete square. The square root will be gone. So this method is called a rationalizing method. Okay, we can also call that dividing out, but it's not really. This dividing out means you factor and then you cross out something. This rationalizing happens when you have square root. You're going to multiply by the same thing on both numerator and denominator. Now let me see what happened. Okay, square root plus minus 3 square root plus 3. It was like a plus b times a minus b. That would be a squared minus b squared. Okay, so you have to know this very, very well. Therefore, we have a minus b times a plus b. So it's going to be a squared. What is this? A squared. That's the square root of x plus 5 squared. You square it, you get x plus 5. Isn't it? All right, now, minus 3 plus 3 was like here. Minus b plus b. You're going to minus b squared. So it's going to minus 3 squared. As you know, it's going to be 9. Okay, now the denominator, I just copy it. X minus 4, that's the first part. And multiply by the second part. I put in the parenthesis, x plus 5 square root plus 3. All right, I can continue. I will simplify this. Limit x minus 4 the numerator x plus 5 minus 9, you get x minus 4. And the denominator, you have x minus 4. I guess you're super happy now because you can cross that out. And the denominator will be x plus 5 plus 3. Okay, once you cross this out, the numerator, you will have a 1. So you're going to have a limit x approach to 4. The top is 1. The bottom is the square root of x plus 5 plus 3. Whew. Can you do direct substitution? Yes, you could. You put in 4 here. So 4 plus 5, which is 9. Square root is 3. 3 plus 3 is 6. So the answer will be 1 over 6. Okay, so this is a little complicated than the just dividing out, because you have to rationalize it. You have to multiply by the conjugate part. And then later, from here to here, you cross out. You're using dividing out method. Okay, so that's 2 examples for that. Now we're going to do the next 1.8 theorem, theorem 1.8. It has a very interesting name. It's called the squeeze theorem. What it says is this: if they give you f of x and know the f of x's value is between, I call this as h of x and the g of x. So this function's value is always between these two. And if the limit x approach to c of this h of x equals L, also limit x approach to c this g of x equals L. That means these two functions, they have the same limit as x approach to c. They have exactly the same limit. And your f is in between them. So you get squeezed, and then limit x approach to c, this f of x will be the same as that. So you understand why it is called a squeeze theorem. It's also called a pinching theorem or the sandwich theorem, because that's right in the middle between these two. Okay, I'm going to give you one example. I give you I give you this, h of x equals negative x squared. And I give you g of x equals positive x squared. Okay, I give you something interesting. I give you f of x equals x squared times sine 1 over x. All right. Based on our understanding about the trigonometric function, we know this. We know sine 1 over x is always between negative 1 and a positive 1. Okay, whatever value, whatever angle or radius here, or radian here, the sign of it is always between positive and negative 1. If I multiply by x squared, can I do that? Yeah, because x squared is non-negative. So if I multiply by x squared, I will get this. Right? That's h. This is a g. All right, now what happened when x approaches to 0? Okay, if just by looking at this, you can say, oh, this is when x approaches to 0, this x squared part is 0. However, we know this. Do you remember this? This is like a shaking, and we cannot get a limit. Remember that part? But we know this part has two boundaries, right? Positive 1, negative 1, and then we multiply by x squared, we get this. This is our h of x. This is my g of x. Now let's see. Limit x approach to 0, negative x squared. What is that? This is a polynomial, so we just direct substitute, we get a 0. And this one, limit x approach to 0, x squared. that's also 0. So if these two functions, h and g, both approach to 0, or their limit as x approach to 0, they have exactly the same limit, then we get this. Limit x approach to 0, x squared times 1 sine 1 over x, that will be 0. See? Instead of find the limit by itself or directly, or sometimes you don't know how to do it, you find the two pieces of bread, which is a little bit greater, a little possible, or a little bit lower, and then both of the upper and the lower functions will approach to the same limit as x approach to that number c. Therefore, you have this limit. So that's what it says, the sandwich theorem, or the squeeze theorem. Okay, next one, the last one. Promise, no more. Okay, so this is a theorem 1.9. It's a very special case, and one is sine x over x as x approaches to 0, that limit is 1. The other one, limit x approach to 0, 1 minus cosine x over x equals 0. So those are the two things, very, very special limits. That's a theorem 1.9. We should be able to prove it. Okay, so how should we prove it? Now think about the sine function. If you have the unit circle you learned a long time ago, that's only a quarter of your unit circle, okay? So this is your angle. We call this is theta, an angle theta. Okay, so this radian is also theta. Agree? This is a unit circle, so this radius is 1, okay? So when you drop down to this x-axis, so this part is cosine theta, and this dotted line, that's my sine theta. If you extend a little bit, that is my tangent theta. Okay, now I'm going to make this a theta approach to 0. So I'm going to drop this line. I'm going to make this line lower and lower, but it's still, you can see what happened is here is my theta is always less than or equal to my tangent theta and greater than or equal to my sine theta, isn't it? So the length of this line, dotted line, is shorter than this curve, and this curve is shorter than this tangent line. All right. Now, if I change that as x, so that will be the x less than or equal to tangent x. Sorry, x. I said x. Sine x less than or equal to that. All right. Now, did you see what I'm going to do? I need to get a sine x over x. Okay, so if I, tangent, do you know tangent x is just sine x over cosine x? You know that, right? Okay, so let me rewrite that. I write x is greater than or equal to sine x, greater or equal to sine x over cosine x. All right, now let's do this. I divided by sine x everywhere. See what I'm doing? I'm proving. I try to prove this theorem. So I divided by x everywhere. Then I get x sine x over sine x, which is 1 less than or equal to x over sine x. Okay, sine x over cosine x divided by sine x. So I get 1 over cosine x. All right, and I just assume this theta or x is a positive, because if it's a negative, then I'm going to change the sign somewhere, but don't worry, we just use positive to show, to prove it, okay? And then I'm going to flip it, because everything here so far is greater than 1. So definitely this part is positive. So I can flip it and then change the direction. So I get a sine of x over x, and I get less than or equal to 1, less than or equal to, flip it, cosine x. Then I get this was squeezed by this two function. So what is 1 as x approaches to 0? It's just 1, isn't it? That's the first thing we learned. And what about this one? Limit, when x approaches to 0, what's the limit cosine x? We can just get cosine 0, and cosine 0 is just 1. See, look, these two pieces of bread, these two functions, they both have the limit of 1 as x approach to 0. Therefore, we get that. We proved it. Limit when x approach to 0, sine x over x. That should be 1. Okay, done. Okay. And what about the second one? How do I prove this one? Let me prove this for you. Okay, I hope you're still awake. Okay. So I need to prove, let me see. Okay. Okay. So I need to, hold on 1 sec. I need to move my paper a little bit. I copy that, okay? Because I think I will not have enough with cosine x over x equals 0. Now, okay, just by looking at this, you cannot use the direct substitution method, because when x approaches to 0, this is a 0. And cosine 0 is 1, so 1 minus 1. We got a 0 over 0 type. And we cannot use dividing out. And we think about it, maybe we can use something looks like the rationalizing method. Okay, so we're going to do this. We're going to multiply by 1 plus cosine. Let's see what happens. When x approaches to 0, and the top I have a 1 minus cosine x, and I do 1 plus cosine x. And the denominator, I'm going to multiply by the same thing, 1 plus cosine x. Okay? And then that equals limit x approach to 0. 1 plus cosine x times 1 minus cosine x. That will be 1 minus cosine square x. Okay, if you still remember what you learned in the pre-calculus 2 about the trigonometric function, 1 minus cosine square, which is going to be sine square x. Okay, so the top is a sine square x over x times 1 plus cosine x. Okay, it's not bad at all, right? Oh, it reminds me something, because we have some sine x over x. So that would be the limit x approach to 0. So this sine square x is just a sine x and a sine x, isn't it? It's just multiplication. And then the bottom here is an x, and here's 1 plus cosine x. Okay, we get a product, and then so that will be this. We already know, we just did it. X approach to 0, and then sine x over x. We know that's 1, okay? So it's going to be more. It's going to be here multiplied by 1, another limit. Excuse me, 1 plus cosine x. This is 1. We know that. Multiply by. This one, when x approaches to 0, the top sine 0 is 0. The bottom cosine 0 is 1. So that is 0 over 2, because of 1 plus 1, that's 2. So what's the answer? 1 times 0 over 2. 0. Done. We proved it. So we definitely proved this one. Okay. Did you see from here to here? I did something looks just like the rationalizing method. All right. Now we learned all those method theorem. We learned so many. 1.8, 1.9. That's what we did. Okay. And we learned the squeezing method. And I didn't write the rationalizing method separately, and we learned what else? The trigonometry. Okay, so we're gonna do something. Give you more example. Okay, so can you find the limit? Find this. Find limit. Okay, so the limit x approach to 0 sine 5x. I just like 5 a lot. Did you notice that? My limit. It looks just like something we did. X approach to 0 sine x over x equals 1, right? But when you have this theorem, and this sign of this guy or x has to be just divided by x, and here it says x approach to 0, but now I have a 5x. What should I do then? It's a sine of an angle. That angle is 5x. If here is a 5x, x approach to 0, what about 5x? 5x of course approach to 0, right? So then I will 5 here, and then I know that will be 1, right? We can just get that 1. So, but you cannot just put a 5 there for no reason. If you put a 5 here, you have to put a 5 somewhere else to make sure that they are equal. It makes sense? Okay, so what it says is this. Limit x approach to 0 sine 5x. Okay, the bottom, I made it a 5x by multiplying by 5, but if you do that, you have to multiply by 5 on top too. Did you see the reason I put 5x here? Because later I want to use that property. However, if you have a 5 here, you have to put a 5 here. All right? Now this is one piece, and this is another piece. So you're going to take 5 out, and then you're going to have limit, and your x approach to 0, then sine 5x over 5x. Okay, so when x approaches to 0, then 5x will also approach to 0. Would you agree? Yeah? So then we can use this property. So I get a 5 times, and that's 1. So my answer is 5. Okay. Or if you like, you can do one more step. You can write y equals 5x. So the limit of when x approaches to 0, the limit of y, which is the limit x approach to 0 of 5x, and that will be also 0. So which means the limit of y is 0. So you can substitute here as y, and here you can put a y. Y equals y approach to 0. So you can do the same thing, but this is how do you use it. Okay? I would like to give you another example. Another one. Find the limit. Okay. X approach to 0. Let me find whether there's any easy one. I mean easy one. This one. Yeah. Tangent square x over x. It's complicated, isn't it? All right. Now this one, and we know tangent. Tangent x will be sine x over cosine x. Okay, so I'm going to write limit x approach to 0, and the tangent square x will be sine square x over cosine square x. Okay, so I'm going to write here sine x square over x cosine square x. Make sense? All right, now keep in mind that we have a sine x over x when x approach to 0 is 1. So I will write this limit x approach to 0. So I just take out one sine. So 1 sine x over x. And the other one, sine x over cosine square x. Okay, so that will be the limit x approach to 0, the first part, sine x over x, multiplied by limit x approach to 0, sine x cosine square x. Okay, now when x approach to 0, this one, we have this theorem, so that's 1. And this one, when x approach to 0, the numerator is 0, but the denominator is not. The denominator cosine x, if you substitute this, is 1. It looks like this. So that answer is 0. Okay, done. So we finished this section. We talked about 2 more properties or 2 more theorems of the limit. Instead of using the direct substitution method, because sometimes we cannot use it, if you substitute, then you're going to get both numerator and denominator to be 0, so you cannot do that. Then we learned how to use the dividing out method, and we learned how to use the rationalizing method. And then we learned 2 more theorems. So one is the squeezing theorem, or sandwich theorem. The other one is a special case. Especially the most important one is this. Most important one is this. Then we learn how to use this to solve the equation, to solve the limit question. Okay, so that is all for this session. It's called evaluating limits analytically. Okay, analytically. All right, that's it.